So, we are now getting into the thickness of what we call as velocity autocorrelation function. Reason we are very interested in this function primarily because with atomic trajectories we are able to find the velocity distribution of the particles. As you know, we first start with the Boltzmann distribution function of the velocity with the equipartition theorem. So, we set up a temperature. However, as we let the system relax and go through various temperature pressure conditions, very important part especially with the phase transition is that we look at velocity autocorrelation function that we talked about in earlier section. So, now looking at the velocity autocorrelation function behavior and its connectivity through Green-Kubo equation at slope as 0, we are able to find the diffusion coefficient and also find whether a material is solid or liquid based on its correlation within the velocities. So, if a material is not if liquid or gas, then you will see it will be a simple decay which is exponential decay, but in other case it will oscillate. So, this is a system which is solid and it shows certain oscillation which is going into backscattering and also looking at asymptotic behavior as it goes to the second correlation. So, this kind of oscillatory behavior is indicative of the solid material. So, if you look at phase transition in case of velocity autocorrelation function, you can simply draw that in terms of how the correlation will look like. So, let us look at this slide. Here we have a correlation function with respect to time, and if you look at the gas will be a straight line. And if you look at the dense gas or liquid, you will see that it's exponential decay and it's going to then become asymptotic. If it is dense gas, it's just going down and becoming asymptotic with the 0 correlation, but it starts with very high correlation. In case of liquid, it goes down exponentially, it decays and then becomes asymptotic to the 0 value. But in case of solid, which is the dotted line, you see that it gets first exponential decay, then it becomes negative and then positive, then oscillates around the 0 value, and that is what is indicative of the solid. So, starting from a rare gas to dense gas to liquid to solid, we have all four phases that we are looking at, and we can identify using velocity autocorrelation function how things are behaving. So, now we are at the stage that we can now use this idea about velocity autocorrelation function to also identify some of the vibrational modes and the transport properties. There are different kinds of transport properties like diffusivity, and when we say transport property, we are looking at the dynamic property. For example, coefficient of diffusion, where we also call as a connection with the viscosity, which we saw one of the VMDL simulation last time. We can also look at the shear viscosity, which is essentially providing viscous effects in when the forces are acting in a sheared mode. So, the forces are acting in a plane which are parallel to each other, but in an opposite direction. That is a shear plane, and you are looking at shear viscosity. Then some of the very common things called thermal conductivity. When you have a material and heated from one side, you will see there is a decay of the temperature as it goes through different thickness based on the thermal conductivity. And if you have three materials with different conductivity K1, K2, K3, then you will see the decay is happening at every three different materials connected to each other. And so, you will have input temperature, decay temperature through these three different walls, and outside temperature, and then you can connect that with the ambient temperature. So, you can see the heat transfer taking place, or you can see fluid transfer taking place, or you can see some stress transfer taking place. Those are transfer phenomena, and that is where we are talking about transport properties. So, if you look at the great advantage, as you see on this particular slide, that there is a continuum equations for it, but we can also convert that into discrete simulation based on the time trajectory. So, diffusivity is given in terms of 1 over volume d rho, which is the density, and the differentiation or integration from 0 to infinite of the velocity autocorrelation from velocity 0 to velocity at time t. And if you look at that, the discrete formula here is V from I is equal to 1 to n, and we are looking at all these velocity distributions at other time t. Now, if you look at the shear viscosity, we can find the viscous term. We are looking at sigma xy and sigma xy at time 0. So, we are looking at these shear stresses in the plane x and y. That is where the shear is happening in the plane x and y, and you are looking at the stress at time 0 at any other time t, and what is their correlation. That gives you shear viscosity. In case of thermal conductivity, you are looking at the heat flux. So, you are looking at the heat flux at time 0 and at time t, and you are looking at the integration of that over infinite time steps in case of integration, but in discrete you have n number of discrete steps, and you are now looking at the kinetic energy and some part coming from configurational energy or what we call potential energy, and looking at that for measurement of the thermal conductivity. So, these are very important aspects that we have to look at, and these are really now getting into the position that not only we can look at properties that are starting from the thermal properties like temperature, pressure, volume, then we went into the properties which are mean square displacement, where you could see the change in phase from diffusion perspective, or you can also look at from structural perspective. So, we looked at G of r, which is radial distribution function. So, now we can expand our horizon to velocity autocorrelation function. So, in the next section what I will do, I will take you through a very simple derivation of what we call a harmonic oscillator, because we are now getting into a specific field of vibrational spectroscopy. So, obviously, we will not get into the quantum mechanics in a much more detail, but we are going to look at some of the properties that we can come up with a simple one dimensional model of what we call as a harmonic oscillator. Thank you.